everyone, my name is Katerina Galitskaya and this is the fourth tutorial in my 6 episode series on antenna simulations and Nullspace. In the previous episode we explored beamforming and looked at how element spacing and phase control affect the radiation pattern. Today we're taking it one step further by adding radome to the antenna array model. We'll look into how to integrate the radome geometry, how to set up material properties, how to do proper meshing, and then how to analyze the radome effect and overall array performance, including gain and radiation pattern. So let's start. And this is where we ended last time with our antenna array with a bit smaller distance between elements to reduce grating lobes and with the 4 element antenna array with a single element as a dipole antenna. So what we do now is we will import radome file. So we can do that from like normal like file import, and we open our step file. For example, in this case, it can be like other 3D formats, but I have my radome step file, and here you have some basic operations with the step files, like you can heal it and so on. So I press finish, and here is my radome. And you can see that it's of course like 90 degrees turned, and sometimes it can happen because the access is different in the different software. So we can either just go into like user interface here and like rotate or choose our volume. Here in the tree you can find the volume number, and you can turn it, for example 90 degrees like this, and it's quite easy. Or you can do the same with journal, right? So in the journal you can also have 90 like turn 90 degree. You can import here. So here I import, of course it's the path will be different for everybody, but then I also want to shift it a bit so antenna is in the center, and then I want to turn everything. So if I run this file now, I will kind of get the same results, but a bit faster than using user interface and like always like press these buttons kind of. So this is my preferred method of interacting with the null space. Let's see, now we have our radome, and you can see that it's quite simple shape. So it's, and this is basically what we really have in real life. It's quite simple shape for base station antennas, for example, right? Usually we don't do anything complicated with the radome. We have some like slanted corners here. That's the maybe most kind of problematic or challenging part of this radome. But otherwise, as you can see, it's quite simple shape. And if we see the mesh here, so we can see that it's very uniform. The only thing is again the corners where it's kind of get a bit not uniform, but otherwise it's quite uniform. And if you can notice here, the antenna elements itself are quite close to the radome. And usually, maybe we try to not have these close antenna elements because we want to have some like a margin, right? For example, for vibration tests and other like mechanical inputs, to have some margin so antenna inside will not be damaged. But it's also so that we try to use the maximum amount of space inside the radome in all dimensions, in the height, in width, and length. So this case that antenna element is close to the like top of the radome is not something unusual. When we have our antenna, our radome like placed as we wanted to place, is we turned and centered. Next step is to assign the materials. And if you can remember, we used to have only one material before, so FR4, because we only needed FR4 for our substrate, and then we also used perfect conductor for antenna and reflector. But in this case, I wanted to have glass fiber for my radome, and this is like a quite common material for radomes because it's very robust. It's very hard. It's good to kind of withdraw all the weather changes and wind and all other things. But what is kind of bad in this case is that it very high dielectric constant and high dielectric losses. So that will affect our antenna as well. And first and foremost, it will affect gain. So this is something that we will need to have a close look at, and just to keep in mind that if we kind of want this trade-off between like robustness of our design, then we will lose something in a gain or antenna performance. Let's look next at simulation setup. So simulation setup is quite similar. It's the same as before. We have our units scaled to millimeters. We have our frequency ranges the same as before. Then we have our radiation, so far field setup. I have 11 frequencies, and if you remember in the beamforming previous tutorial, I had step as 1 degree to have a bit more accuracy in the radiation pattern. So while beamforming, but in this case, I will have only like not no beamforming. I will have all in bore side steering. So I went back to 2 degrees to just kind of save something on simulation time. And I assign as usual my simulation scans, my scan angles, and that's it basically for the simulation setup. Let's look at the post processing. So in the post processing, I go with the new model that I just created with the radome in it, and then I retrieve all data that I want, right? I go with the S parameters if I want, then I want, of course, in antenna case, we talked about this before, I want active S parameters. And again, I want to excite every port as equal here. In this case, we already looked at the beamforming, how to have amplitude tapering, how to have phase tapering. So in this case, I don't need that. I only want to excite all my ports equally without any phase shift. So I have active as parameters for each port. I want to have like not combined active parameters, but for each port separately to see how location of the element affect the active as parameters, and also maybe there is some radome effect as well. And then if we look at the gain setup, so I want to have my bore side gain, of course, and then what I want to see if is difference between no radome setup and with the radome, right? So that's what kind of we are interested in, what we are losing. And I from previous tutorial when we worked with beamforming, I just saved txt file with the gain versus frequency, and I imported in here. You can see here I loaded this data and then plotted it with the current gain versus frequency to have this comparison. And then I plotted the usual elevation pattern and 3D pattern. So let's look at the results. You can see that active parameters, again, we have different active parameters, different for each port. So this is one more time I remind you that it's always good to control active parameters for each port to have a close look on that. And it's not unusual for us to kind of see that there is difference between edge elements and central elements in antenna array in terms of coupling and matching. So active parameters will say exactly that, and it's also sometimes it's you can see that, for example, you need to tune edge elements differently and have maybe several versions of your element in antenna array, but that's completely normal to have best possible matching when all combined. And the most important plot here, the most interesting one, of course, is the gain versus frequency. We have this dashed yellow line is with no radome, and then now we have our blue line is with the radome. You can see that there is very big gain drop around 2 dB or something. That's very much. Usually, of course, we cannot afford that in the real case scenario. So we go with the something like we have not maybe so thick radome. We maybe don't place an element so close, so we cannot afford to lose 2 dB on just radome. But this is like very extreme case when you can, but you can see that it's actually there is this effect. You cannot just take a radome, simulate your antenna without radome, and then just assume that you will place the radome like, and it will not have any effect. It will have effect, and you can see here that even the gain curve is changed a bit. It's not only like the amplitude kind of the it changed. It's also a bit the behavior of the antenna changed. So that's very important to keep in mind. And then when it comes to the radiation pattern itself, I wouldn't expect any changes here. Usually, when we kind of don't plan for this, when we don't design like the electric lens, like specifically or something, we don't want this effect. We usually want like radome to kind of have to be kind of like very like transparent structure for antenna, as transparent as possible. If we don't want any specific properties from that, of course. So in this case, did not expect any changes in the radiation pattern, and we don't have any changes in radiation pattern. And we also can see it on the 3D radiation pattern that it looks as we had it before with without radon. So this was today's tutorial. I think that I wanted to show this kind of very drastic case, like very extreme case when the radome actually can affect so much. You can lose so much gain on the radome, and of course you will also have a lot of different losses besides that, like a feed network, cables, and so on, so on. So it's very important to have that in mind, and. I hope that it was interesting and insightful. In the next episode, we will go into electrical large simulations and do some integrated antenna design when we integrate antenna on towers and see how antenna array perform there. And I hope that it was interesting, and have a nice day. Bye bye.